So hi, we are now in the middle of discussing astrophysical applications. You'll be happy to know that we are comfortably past the stage where we've discussed most of the basics of fluid dynamics that are needed to understand certain applications to astrophysics. Specifically, we have already, we are discussing this thing, transonic flows in astrophysics, right? In other words, flows that transition from subsonic to supersonic. That's what transonic means, right? Okay, so this is what we're discussing, and we have there are several applications, and we have already just discussed this, jets from compact objects, and the application of the concept of a de Laval nozzle to that, right? And the next thing we will discuss is this. We will discuss two things at the same time, two very disparate, two very different astrophysical situations, the solar wind and spherical accretion onto compact objects. We will discuss this both at the same time. And then we will discuss supernova shocks, and in particular we will discuss one particular kind of solution to the supernova shocks, which are called Sedov-Taylor self-similar solutions. We will explain all this terminology when we get to it, right? So the important distinction I want to make between these two applications and the third one is that the first two applications these two involve smooth, i.e. shock-less flows, whereas the third one obviously involves shocks. Right, so there is a conceptual difference between these three, but we are now having studied compressibility and the speed of sound, and in particular transonic flows, we are and also shocks as we along the way, we are in a position to handle all these three applications. Okay, and time permitting, we will also discuss accretion disks onto. So this would be spherical accretion. There's also something, accretion also happens in the form of a disk, and so that also involves a fair amount of fluid dynamics concepts, and so we will also discuss accretion disks as we go along. So let us first consider this. Well, we've already considered jets from compact objects. We're done. The number 2 is done. Now let us go on to number 1 here. Yeah, so what are transonic flows? We already said this, but no harm in emphasizing this a little more. Simply put, flows that transition from being subsonic, in other words, from Mach number less than 1 to supersonic, Mach number greater than 1. Supersonic would be this, and subsonic would be this. Or, for that matter, supersonic to subsonic, either way. Okay? And this transition can be either smooth or via a shock. In particular, generally shocks tend to address this kind of situation. So you realize how shock flows as well as smooth flows, smooth transition flows, both of them fall under this transonic category. Okay. They generally exhibit counterintuitive features. Okay, we've seen, for instance, in our discussion of the de Laval nozzle, how some of these flows can be quite strange. Okay, diverging nozzles lead to accelerating flows when they're supersonic, and so on and so forth. Yeah, so we first consider outflows from or accretion onto a spherical object. Okay, probably good to sketch this a little bit. So what do you mean by outflows from a spherical object? Well, consider consider a compact object. A very compact astrophysical object such as black hole or a neutron star for that matter. Now what's with this? What's special about this? There is an extremely compact, in other words, extremely high density object sitting here, like so. So it's quite massive, but because it's very high density, it's almost a point object. It's really small. Okay, now what does this do? You put an extremely high density object in the middle of the interstellar medium, which is not empty, as we always say. Outer space is not empty, it's just very thin, very tenuous. Okay, so on account of its high mass, it attracts the matter. Simple gravitational attraction. Okay, it attracts matter around it. So matter because the central object is so massive, it attracts matter, in particular gas, from around it. Another way of, and the matter gets attracted, and it either, in case of a neutron star or something, it settles on the central object, or in case of a black hole, it gets swallowed by the black hole. So this process of attracting and accumulating matter onto it is called accretion. Look up if you're not familiar with the word, you can look it up, the dictionary meaning of it. Accrete means to accumulate. So because the central object is so massive, it attracts matter from around it, yeah, causing it to accrete. We will consider the special case of spherical accretion. Why? Well, partially because it's astrophysically important. There are many situations where there's an isolated black hole just sitting there by itself, and so it accretes in a quasi-spherical manner, right? And also because the spherical symmetry leads to several mathematical simplifications, so it's simple. Okay, so this is one thing we will consider. This is the first situation. One situation we will consider is one situation. The other situation we will consider is the sun, the outer atmosphere. Now the sun, you realize, is nothing like a black hole. It's just a regular star, and it's not all that massive. It's just one solar mass, right? But the main thing about it, the outer atmosphere, of the sun, our sun, which is called the corona, which is very thin and quite hot, and it's not directly visible to us except during eclipses, right? Is very hot and tenuous, very thin. Okay, and what happens is you have the sun, yeah, and its outer atmosphere out here, say, right? It's so hot, okay, that the pressure there is enough for it. The outer atmosphere is so hot that it can actually escape the pull of the sun's gravity. It's somewhat like water boiling off of the surface of a pan that you keep. The outermost surface of the boiling water, the molecules there have enough kinetic energy, okay, to escape, and they go off, right? It's somewhat like that. It's a little more detailed than that, and we will work out the mathematics, but still. Okay, so that's what happens here. The outer atmosphere is so hot that the outer atmosphere essentially escapes. Escapes in a spherically symmetric fashion, at least to first degree. It essentially escapes in a spherically symmetric fashion to form what is called the solar wind. So there's a wind blowing out from the outer atmosphere of the sun, okay, and as such the wind permeates much of the solar system. Certainly it flows past the Earth, okay, and the solar wind, I think it's been observed as far as the orbit of Neptune. Okay, so now by way of cartoons, notice the similarity between this and this cartoon. Here too there's a spherically symmetric inflow, whereas here there's a spherically symmetric outflow. Okay, so what we're going to do is we're going to study spherically, so it's simply, spherically symmetric inflows and outflows. You just reverse the direction of the arrow, one becomes the other, right? So we're going to study spherically symmetric inflows and outflows that are transonic. That is our brief. Okay, in case of the sun, the outflow starts out being subsonic from very close to the sun, very close to the outer atmosphere of the sun, which is the corona. It essentially starts from rest. Okay, it has a finite velocity, that's why it's boiling off, but it starts out subsonic and it accelerates and it becomes supersonic. Whereas here what happens is this is a spherically symmetric inflow, and very far from the compact object, the stuff, the gas is essentially at rest. So it was subsonic, and as it gets attracted towards a compact object, it gains speed and it becomes supersonic. Either way, these are transonic flows. Okay, so this is the subject of our discussion. We will first consider outflows from or accretion onto a spherical object. So in spherical geometry, the first thing we consider is mass conservation, and we say rho is the density, u is the velocity, and r square is simply the radius in spherical coordinates, and we say rho u r squared equals constant. So as with everything, we call this mass conservation, but what is it really? Conservation of what, right? So the rho is in grams per centimeter cubed, isn't it? So that's what the rho was, right? The u is a velocity, so you have centimeter per second, and r squared is essentially centimeter squared. So you can see that we are really discussing conservation of mass per unit time, grams per second, the centimeters. So where did this r squared come from? Well, what you do is you consider the mass flux into a sphere. And the mass flux, you remember, is grams per centimeter squared per second. Okay, and what's the area of a sphere? It's 4 pi r squared. Right? So you multiply the area with the mass flux and you get, so that's where the r squared comes from, and you get mass per unit time. And the constant, the 4 pi is simply absorbed into the constant. Okay, so that is where this thing comes from. Okay, but as with our discussion of the de Laval nozzle, this integral statement is not as useful to us as the differential statement. Okay, so this and this are essentially equivalent. Okay, this and this are the equivalent statements. What you simply need to do is differentiate both of these with respect to r, and assume that everything, the density as well as the velocity, is a function of r. Okay, so you get this. So differentiating a constant gives you 0, so that's what you get here. So this is the first equation, first important equation. So this is the mass conservation equation. And we next consider the momentum conservation equation. We neglect viscosity. We consider inviscid flows. But in several applications that we were considering so far in lab situations, we were neglecting body forces. Okay, you consider, I don't know, water in a container or so on and so forth. The height of the container is so small that, variations in gravity are negligible. So gravity was most of the time neglected in our discussions of lab fluid dynamics. Whereas here, of course, gravity is of utmost importance. Gravity is important. This is what drives everything, really. Okay, for a compact object, it's gravity of the central object that causes matter to accrete. Okay, and for the sun, it's a fact that the gravity of the sun is continuously trying to hold back the outer atmosphere, but the outer atmosphere is hot enough such that it kind of evaporates, and so there's a competition between that and the gravity of the sun. Okay, so these are of utmost importance. So gravity is now considered. Okay. Yeah. So the momentum equation, now you recognize the dp dr, and this is the inertial term, and this is the body force term, right? So this would be inertial term, pressure gradient. We don't know what the pressure is yet. We will solve for it. Okay. Pressure gradient term. And this is body forces. Due to gravity, of course. Right? And we don't consider surface forces because we are now only dealing with inviscid flows. Okay, so these are our two main equations, mass conservation and momentum conservation. We do the usual trick. We use the speed of sound, the definition of the speed of sound, this one, to eliminate p in favor of rho. You see here you have the p. Right, so why do that? Use the speed of sound to cast this in terms of rho, like this. So you just use a chain rule, essentially. And you can combine this equation and that equation, and I strongly urge you to work it out to obtain this all important equation. This is all we'll really need for the time being. Okay, so this is the main equation that we will be working with from now on. And yeah, so what we will do in our subsequent discussions is we will look at the parameter space spanned by this parameter space of allowable solutions that are predicted by this equation, to investigate. So this would be R here, and this would be the square of the Mach number, or U squared over, okay, so U squared over C sub S squared as a function of R. Okay, there are several allowable solutions that are predicted by this equation. Okay, what you really need to do is, of course, find out U of R. In order to do that, what you do is you take this du dr, you take it to the right hand side. Du dr is equal to this term divided by this term, isn't it? And you integrate it, and you'll have a constant of integration. Okay, and depending upon what that constant of integration is, you will find you will arrive at different solutions, and these represent different possible solutions. You have several classes of solutions. You have a solution that can look like this. You have a solution that can look like that. You have solutions that can look like, so this would be solutions of nature 1. This is solutions of nature 2, and these are another kind of solution which is called solution 3, and these would be solutions of the type 4. These would be solutions of the type 5, and there are 6 different kinds of solutions. Six different kinds of solutions that are allowed by this equation. And what's the main thing that distinguishes one kind of solution from the other? Why do we divide it into 6 categories? Because this dotted line corresponds to m squared equals 1. In other words, Mach number equal to 1. If the square of the Mach number is equal to 1, the Mach number itself is also equal to 1. So upwards of here you have supersonic flows, downwards of here you have subsonic flows. Subsonic flows, sonic point, so to speak, and supersonic flows. Okay, so this represents a parameter space of acceptable transonic solutions to this equation here. Why is this spherically symmetric? Well, you know, the conservation of mass, this essentially arises from 4 pi r squared times constant. That's where you got this, right? And 4 pi r squared is the area of a sphere. You're assuming that the mass flux is distributed symmetrically on the sphere, either outgoing mass flux or incoming mass flux. Okay, and in the momentum equation, you see you just have one coordinate r, just one coordinate r. This is spherically symmetric gravity, and you only have, so spherical symmetry is invoked in this equation as well as this equation, which is why, you know, spherical geometry. And so this is essentially this will, you know, tell us the character of that we can expect from different kinds of transonic solutions, okay, due to either accretion or excretion or winds in spherical geometry. And we will discuss the nature of each of these solutions in detail. So that's it for the time being, and thank you.